Section 6.2 is solving systems using substitution. I can solve systems of equations using substitution. Big ideas for this section. Systems of equations can be solved in more than one way, and when a system has at least one equation that can be solved quickly for a variable, the system can be solved efficiently using substitution. When we solve systems, guys, we're still trying to find our x and our y, and yesterday we did that with graphing. But what we're trying to do here is to use substitution. Sometimes we're going to have values that aren't necessarily easy to graph or easy to find on a graph, where we'd have to estimate between 1 and 2 or where the values are. So if we use algebra, we can solve these to get exact answers every time. So if we look here, we know that y equals 3x. So since I know that, everywhere that I see a y in my other equation, I'm going to substitute in 3x. So I keep my equation exactly as it's written, except that when there's my variable that I have, here I have y, here's a y, I plug that value in for 3x, of 3x. And again, we keep the rest of it exactly the same. So the only thing I changed in my equation here is that I traded out my y for what I know it is, 3x. The idea here, guys, is that we're trying to get one equation that just has one variable in it. Here we just have x's, because then I can solve it. I can simplify each side, okay? Combine my like terms. 1x plus 3x gives me 4x. And to get rid of my x, I divide by 4 on both sides. X equals -8. Just like when we solved with graphing, though, we need to have the entire ordered pair. So we have to substitute back in to find our y value. And x, we said, was -8 from right here. So y is going to be -24. We write that as an ordered pair still, x and then y. Again, we have two variables. I have y's and x's, so I need to have both x's and y's in my solution. We can plug those back in and check. In my first equation, y equals 3 times x, -24 equals -24, check. And x, -24, plus y, -8, equals -32, and that checks as well. So our solution is correct. That is the only set of values that are going to make both of these equations true. Go ahead and pause it here. Give it a try. Okay, so this one looks just a little bit different in that both equations are solved for y. Y equals 2x plus 7 and y equals x minus 1. So it doesn't matter which one, but I'm going to use the top equation to substitute into my second equation. I know that x is 2x plus 7, that y is 2x plus 7, so I'm going to substitute that in for y. Now my y, instead of being a y, is this 2x plus 7. But the rest of my equation stays exactly the same. Now we just solve. X is on both sides, so I'm going to subtract to get them together. X minus x is 0. I have x plus 7 equals -1. Remember, the sign goes with the number. Now I can subtract 7 to get the x all the way by itself, and I get -8. Once I know my x value, I can plug it back in to find my y value. It doesn't matter which equation we plug it into here. And just like when I substituted before, everything stays the exact same except for where I plug that value into. So y equals -16 plus 7. Y equals -9. So my ordered pair, again, always x and then y, is going to be -8, -9. And if we plug those into our equations, it checks out. In example 2 here, when we solve for a variable first and then use substitution, when we look at this system here, it doesn't look like it's solved for a variable yet. We don't have x equals a value or y equals a value. We have to find that. And in order to do that, we're going to compare our coefficients. Here I have a 3 and a 4 and a -2, and here I just have a 1. There's nothing that I would have to divide by. So this y right here is going to be the easiest thing for me to solve for because there's no number in front of it. There's no coefficient, it's just a y. So it's only one step to solve for. I can add 2x, and I'm not going to have any extra fractions. When I do that, keep in mind that because the -3 doesn't have a variable and the 2x does, I can't combine them. So I'm just going to write it as 2x and a -3. I can add them and keep them as two separate terms, but I cannot combine them into one because they do not have the same variable part. Now, I know what x is. X is 2x. Sorry, I know what y is. Y is 2x minus 3. So I'm going to take that and plug it into my other equation. I used this one, so it has to go into the other equation. Everything stays the exact same except for y. Because y I know. I know that y is 2x minus 3. So again, the rest of our equation we bring down exactly as it's written. The 3 plus 4x and equals 14. To solve our equation here, first step is going to be to distribute the 3 into my parentheses. 3 times 2x is 6x. 3 times -3 is -9. Plus 4x equals 14. I can combine my like terms here. And remember, we can't cross the equal sign until each side is as simple as we can get it. 10x minus 9 equals 14. Now, left side is as simple as we can get it, right side is as simple. So we can solve by adding 9 and moving from one side to the other. And then divide by 10. And x is going to be 2.3. Now that we know x, we can solve for y by plugging it into our equation. So y equals 2. Again, x we know is 2.3. And the rest of the equation stays exactly the same. And we get y equals 1.6. So x is 2.3 when y is 1.6. Remember x and then y. Now feel free to pause and give this a try if you'd like. Okay, when we compare our variables, I have a 6y, a 5x, a 3y, and just an x. The easiest one here to solve for is just the x because there's no number in front of it. So that's the one I'm going to solve for. In order to do that, I have to subtract a 3y. It's being added, we get rid of it by subtracting. And just like on the last example, I cannot put the -7 and the -3y together because they're not like terms. They do not have the same variable part. So minus 3y minus 7. You also could have that in the reverse order if you'd like. Now that I know what x is, I can substitute that in. I know x is this. As long as I go into my other equation, I can plug that in for x because I know x equals that. Everything in my equation stays exactly as it's written until I get to the x. And instead of writing an x, I'm going to write the 3y minus 7. And then continue my equation exactly as it's written. Now I have one equation and it only has one variable in it, just y's, so we can solve. First step, going to be to distribute and bring down the rest of the problem. We can combine like terms. Now I can add 35 to get the y's by itself. And then divide by -9. So we're going to keep y as -43 over 9. You also could write that as -4 and 7 over 9, or -4.7 repeating, but we don't want to round. We want the exact answer because we still have to plug that back in to find x, and we want it to be exactly right. Once we have y, we still have to find x. We have two variables in our original equations, so we have to have two variables in our answer. X equals -3. Y, we know, is -43 over 9. And again, the rest of our equation stays exactly the same. So we multiply there over 1 straight across. We get 43 over 3 minus 7. 7 I can rewrite here as 21 over 3. So I can take 43 minus 21 and get 22 over 3. We can also write that as 7 1/3 or 7.3 repeating. So in my final answer, I'm going to have 22 over 3 and -43 over 9. A real quick recap over the first part of section 6.2 here. Systems of equations can be solved in more than one way. When a system has at least one equation that can be solved quickly for a variable, the system can be solved efficiently using substitution. And that's all for the first half of section 6.2.